Okay, in this experiment, we're looking at diffraction off of a CD. And I've set up essentially a protractor on this screen here so that the lines will be projected on here against the white background so you can see where the beams are going. Before I get to the CD part, let's just think about reflection, pure old reflection off of a surface. If I take my laser pointer and I shine it down the 30-degree line here, it comes up the 30-degree line on the other side, right? That's just the law of reflection. It's just reflecting off of my countertop. Okay, if I went at 60 degrees, let's see if I can keep it at 60 degrees, the reflected beam, it's hard to hold it at 60 degrees, the reflected beam will come up at 60 degrees also. Okay, so that's just pure old reflection. Now, when I put a CD surface, we're not going to just use any CD. We have the Beatles' The White Album. If you look at any CD on this side, you're probably seeing rainbow patterns in the disc, right? That's because songs are actually etched into the disc of the CD by little pits and grooves, okay? And the light bounces off of those pits and grooves, and that is the information of the music. The music is stored in that information. And then a laser reads the CD, and it can tell how deep the groove is, or where there's a groove and where there's a ledge. And then it converts that information into sound again. Well, those pits and grooves mean that light reflecting off of the surface is bouncing back off of different heights, and it's sort of like thin film interference again, where you have beams reflecting from different points, traveling slightly different paths, and so they can interfere constructively or destructively. All right, so I've set this up so that I can slide the disc under here like this. Okay, and I'm sliding it through, so I'm going to go across. The grooves are etched into the CD around in the circle, and so I want to go across the groove, so the beam will span different rows that are etched into the CD. So let me just show you what happens when you do this. Okay, so we'll go down like the 30-degree line. Look at that. Okay, so we're getting all sorts of different lines coming out. Obviously more than just the pure reflection that you would get off of any other surface. Okay, that's the diffraction of the CD. So what I'll do here is I'll hold the laser at a few different angles. We'll pick like 3 different angles. And I'll do it with the green laser and with the red laser. At each one you can pause it and read off the angle of the different beams. And in the lab handout, I'll explain what the different beams, how to label them and put them into the spreadsheet. And then I'll also do an explainer video once this data has been collected, showing you how to enter in one of the angles. All right, so let's see. I'll start out from closer to 0, and then I'll move down. When you're recording the angles, I think you can see on the screen that there's little dots in between. Each dot is 5 degrees apart. Our uncertainty in this experiment is somewhat large, so you should be able to tell whether the diffraction line is in between one of the dots or between one of the dots and the line. But better than that, it's going to be hard. My hand is only so steady, and my alignment with the same point on the disc is only so perfect, which is to say not very perfect. And so there's a margin of error here. But I would try to record where the line is within that 5-degree range. Okay, so let's start out at 15 degrees. Okay, so I'm going to try to shine straight down the 15-degree line. Okay, and so you can see the diffraction pattern here, and pause it at any moment to record the diffraction pattern at 15 degrees. Okay. So obviously not all the lines are shining equally high, and you're going to have to do a little bit of extrapolation to record them. But overall, you should be able to get a decent estimation of where that line is. The trick is knowing, is this the m equals 1 or 2 or 3 or minus 1? Okay. Well, so that's 15 degrees incoming. Now let's do 30, and then we'll do like another one down here. Maybe we'll do 60. All right, so 30 degrees. So I'm going to try to follow it down. 30 degrees. Okay. So that is the pattern for 30 degrees. So you can pause this at any point and record where those lines are. All right, and then lastly, let's do 60 degrees. Oh, why don't we, with the green, we'll just do all 5 of these lines here. So we'll do 45. Okay, so that's 45 degrees. And now 60. Okay, so that's the 60-degree diffraction pattern. And then lastly, let's do 75-degree diffraction pattern. Okay, so that's 75 degrees right there. Hard to hold my handle at that angle. Okay. All right, so we've got a whole set of data for the green. Do your best to put the angles where they should go. With the red's not quite as bright. I'll probably skip the intermediate angles. So let's do 15, 45, and then 75 for the red laser. There will be a difference because the red laser is a different wavelength than the green. Okay, so this is 15 degrees with the red laser. Okay, so that's the diffraction pattern for 15 degrees. 45. Okay, so you can see where there's at least 4 lines there for 45 degrees. And then try 75. Okay, so they're pretty faint, but I can see at least 4 lines there at the 75-degree mark. Okay, so one is around here. I don't know if this one will be that visible for you. Actually, maybe there's one over here too. All right, so those are the data points. So we have 8, I guess, different data points that you can use to analyze the data. The spreadsheet will be all set up. The trick is recording the angles, putting them in for the correct M values, and then that information will allow you to figure out how closely together spaced the grooves are on the CD. And I'll put together a second video that shows how I make those measurements of the diffraction lines and enter them into the spreadsheet. So I'll probably do one series of, maybe I'll do a couple of different angles, a couple of different starting angles to show you how that all works.